Now, to further illustrate the generation of the currents in the extracellular space resulting from a particular synaptic input current in a neuron, we show this simulation. There is a synapse right here that in the simulation induces this synaptic current. Those currents are relatively small, in the order of picoamps. So we have a synaptic current here. And we can now calculate, for instance, at two different positions, phi 1 and phi 2, the change in the voltage in the extracellular space as a result of this synaptic input current. And you can already see from the shape of the simulation that this indeed looks like a current dipole. Now, very close to the synaptic current, this is the voltage change that we measure in nanovolts. And if we go to the other side of the neuron, the voltage deflection is the other way around, which is to be expected because of the current dipole nature of this particular neuron. Of course, it's not a perfect dipole, current dipole is seen here, but you can approximate it by a current dipole, which is indeed what we will do. Now, this was a measurement very close to the neuron, and what would be the voltage if we would record at the skull? So this again is our neuron, this is the position of a synaptic input. We added the cerebral spinal fluid, the skull and the skin with the correct conductances or the estimated conductances. And we have a small current dipole, and the size of the current dipole is indicated in the upper graph. And as it has three directions, x, y, and z, there are three curves are shown. And in this case, the z direction is the largest. It's about 15 nanoamp per micrometer, the size of the current dipole, and that results in changes in the voltage at the skull of the order of picovolts, 10 to 20 picovolts. So this is the result of a single cortical pyramidal cell that receives this particular input. Now, clearly we don't measure picovolts, so there must be much more synapses active, and in addition, we actually record activity of many more neurons than a single neuron with our EEG. Otherwise, we would not be able to measure. We cannot reliably measure picovolts at the scalp. The voltages that we record are of the order of microvolts, which is 1 million times larger than the picovolts. And the main contribution to the larger voltage is that we record for many more neurons that are aligned in parallel, generate to some extent parallel dipoles, current dipoles, and are to some extent synchronized. So the current dipoles at a particular moment in time are not completely, but to some extent, synchronously active. And this is illustrated in the two cartoons here on the right. We have several pyramidal cells. Each is a little current dipole, which results in a measurement at the scalp that is larger than a single one and larger than zero. And this illustrates why orientation is important, because if the pyramidal cells would be oriented like this, for instance, or in completely random order, then at a particular distance from this assembly, we would not measure an effective change in voltage, as the current dipoles essentially cancel each other, which is known as a closed source field. So the pyramidal cells are aligned, parallel, creating an open source field, and the various current dipoles of each individual neuron can be added to some extent, and they are synchronously active, and that eventually results in a measurable voltage at the scalp, or even at the on the surface of the brain. Now you can calculate how large that is, and this is further detailed in the book. So you can calculate the voltage generated by a cortical column, where we assume that in this cylinder there's a particular density of pyramidal cells aligned in parallel, and there's a particular distance from the recording electrode, and that eventually results in approximately 1 to 2 millivolts given a particular density of neurons and an excitatory input current of 200 picoamps. Now that indeed becomes a little bit more in the range of what we measure. In fact, we measure microvolts, but note that we measure voltage differences, differences that are of the order of 10 to 1 to 300 microvolts. So those are the voltages that we can measure with the scalp EEG. So if we record an EEG in the clinic, and an example of that is shown on this slide. On the right, you see a healthy control whose brain waves are recorded with an EEG cap, and in the left upper panel, the rhythms are shown as being recorded. This is 1, 2, 3, 4, 5, 6 seconds. And what I forgot to denote here, but this is approximately 100 microvolts. So this is macroscopic EEG resulting from the collective action of many cortical parallel aligned cells, and those are mainly the pyramidal cells, as shown here, where each cell can be viewed as a little current dipole, and it's thanks to the parallel alignment and in part the synchrony between the different pyramidal cells that the currents indeed add, resulting in a sufficiently large extracellular current that gives rise to small voltage fluctuations at the level of the scalp that we can measure with our EEG electrodes. And this was all discovered by Hans Berger at the beginning of the last century, around 1924, and he performed part of the measurements on his little son Klaus, who was, I think, about 11 years old at that time. And this is another illustration of EEGs. On the left, a 4-second epoch, and on the right also 4 or 5 second epoch, where on the left the eyes are closed, EC, and on the right the eyes are open, EO. And you immediately observe that there is a big difference between eyes closed and eyes open. And this phenomenon is known as reactivity. And another observation is that brains are never at rest. You continuously see activity. There are rhythms all the time, which is a sign of a normal brain. And you also find, and you can look in the book or other literature what this means, but in short, even numbers refer to electrode positions on the right side of the brain, odd to electrode positions on the left side of the brain. And this is frontopolar, this is temporal, this is occipital, and C is for central. You immediately observe that there's also a spatial gradient. So different parts of the brain generate different rhythms, both in frequency and both in amplitude. And what is also noted, and that's on the panel here, is this deflection, particularly seen in the frontal channels. So this is frontopolar on the right side, on the left side, and again on the right side, on the left side. This is a particular way to represent the signals, known as a montage. And what is shown on the right is an eye blink. So the EEG also measures, or during an EEG measurement, you will also record eye blinks. And you can look in the literature to figure out what the cause of this eye blink artifact, as it is known, is. So the voltage differences that are measured by the EEG once more reflect mainly activity in the cortex, in the pyramidal cells. And maybe it is fortunate that the cortex behaves very differently in different physiological, but also in many pathological conditions, which makes the EEG such a wonderful instrument to measure the integrity and the function of the cortex. And what is shown here on the left are 4 different rhythms that we can observe in, for instance, an excited state, in a relaxed state, during drowsiness, during sleep. So this is sleep stage 2, these are sleep spindles, and this is deep sleep. So the cortex really generates different rhythms in different physiological states, reflecting different activity of all the cortical neurons. And we will see later that in pathology, we can also find very, very different rhythms that can assist us very much in the diagnostics of various neurological disorders and can also assist in prognostication, to just name a few. And here, some other applications for the EEG in the clinic are shown. I just mentioned diagnostics, which is very important in patients who may suffer from epilepsy, and also for the classification of epilepsy. The EEG is also very useful to guide the neurosurgeon during epilepsy surgery. It is a very important tool to measure the quality of sleep. It's used for diagnostics in developmental disorders, and it's extensively used for monitoring brains in the operating theater, because if the patient is sedated, anesthetized, then even in those conditions, brains still generate rhythms, and we can use the rhythms, for instance, to measure whether the brain still is perfused sufficiently with the needed blood containing the oxygen and the glucose. And it's also increasingly and extensively used in the ICU to monitor patients, for instance, after traumatic brain injury or with a post-synaptic coma, to assist in detecting of seizures, for instance, and prognostication. Several of these applications will be discussed in later lectures. For now, thank you very much for attending, and this is the last part of this lecture on some fundamentals of the EEG.